Okay, good morning. Welcome to class. Today, let's have a look at the second lesson of chapter 5. Today, we're going to talk about operations with geometric vectors in two space. Two space means two-dimensional space or 2D space. First, let's have a look at learning goals. After this lesson, you are expected to be able to apply addition, subtraction, and scalar multiplication to geometric vectors in two space. Solve problems related to vector addition, subtraction, and scalar multiplication geometrically in two space. Determine if vectors are collinear in two space, and understand the distributive, associative, and identity properties for scalar multiplication for geometric vectors, and apply them to solve related problems in two space. And last, understand the concept of linear combination of vectors in two space. Okay, so first of all, let's have a look at an introductory example. When we add two or more vectors, we are finding a single vector called the resultant that has the same effect as the original vectors applied one after the other. For example, if you walk north 800 meters and then west 600 meters, the result is the same as if you walk west of north 37 degrees. So note that arc sine 0.6 equals approximately 37 degrees. For 1,000 meters, the resultant vector is often represented by the symbol R. So basically, we want to have a rule for vector addition, right? So there are two methods we can find the resultant vector. First, let's consider the triangle method for vector addition. So consider two vectors A and B like this. Think of A plus B, vector A plus vector B, as A followed by vector B. We can translate vector B so that the tail of vector B touches the head of vector A. Then we can find the sum by drawing and measuring from the tail of vector A to the head of vector B. This new vector is then the resultant vector A plus B. This is called the head-to-tail or triangle method. Any questions? So this is how you can find vector A plus vector B. Okay, then there is another method called the parallelogram method. Again, consider two vectors A and B like this. Translate vector B so that the tail of vector B touches the tail of vector A. Then we can complete the parallelogram that has vector A and B as two of its sides. Because of the properties of parallelograms, vector B and vector V are equivalent vectors. Thus, vector A plus vector B equals vector A plus vector V. Use the head-to-tail method above to find vector A plus vector V. The resultant vector A plus vector B is the indicated diagonal of the parallelogram. This is called the tail-to-tail or parallelogram method. So there are two methods. You can find vector A plus vector B, right? You can choose either one you like. Any questions? No? Okay, then next let's have a look at some properties of vector addition. First, vector addition has commutative property. That means you can change the order of addition, such as if you have vector A plus vector V plus then plus vector W, that equals vector U plus the sum of vector A and vector W. You can change the order of addition. Also, the vector addition fulfills associative property. That means the sum of vector U plus vector V equals vector U plus vector V. You can change the order of the two vectors. So this can be easily proved by using the triangle method or parallelogram, right? Parallelogram method. The rigorous proof of these properties involves the concept of Cartesian vectors, which we will learn in the next few lessons. You can try to prove these properties after we have learned the concept of Cartesian vectors in our next lesson. Or actually the lesson after next lesson. You have any questions? Okay, then let's have a look at a special case, adding parallel vectors, same direction. So suppose we have vectors A and B that are parallel and have the same direction. Vector A is 5 kilometers per hour east. Vector B is 7 kilometers per hour east. To find vector A plus vector B, you can place the tail of vector B at the head of vector A, right? The resultant is the vector from the tail of the first vector A to the tip of the second vector B. So as you can see here, because these two vectors have the same direction, so the resultant is 12 kilometers per hour east. From the diagram, we can see that to add parallel vectors having the same direction, we can just add their magnitudes. The resultant has the same direction as the original vectors. Any questions? All right, then let's have a look at another special case, adding parallel vectors, opposite direction. Again, suppose we have two vectors C and D that are parallel but have opposite directions. To find vector C plus vector D, you can simply place the tail of vector D at the head of vector C. The resultant is a vector from the tail of vector C to the head of vector D, right? From the diagram, the magnitude of the resultant is equal to the magnitude of vector C minus the magnitude of vector D. The direction of the resultant is the same as the direction of vector C, or northeast. because apparently vector C has larger magnitude, right? So in general, for parallel vectors A and B having opposite directions and their resultant vector R, we have the following relationship. If the magnitude of vector A is larger than the magnitude of vector B, then we have the magnitude of vector R equals the magnitude of vector A minus the magnitude of vector B. And R has the same direction as A, right? Then if the magnitude of B is larger than magnitude of A, then the magnitude of R equals the magnitude of B minus the magnitude of A. And R has the same direction as vector B. This is pretty straightforward, right? Okay, have a look at this. Any questions, just let me know. Okay, so far we have talked about the rule for adding vectors, right? So next, let's have a look at the rule for subtracting vectors. Well, actually, you can consider subtracting vectors as adding a negative vector, right? So first of all, let's have a look at the head-to-tail method. The relationship between addition and subtraction with vectors is similar to the relationship between addition and subtraction with scalars. To subtract u and v, vector u minus vector v, we can add the opposite of vector v to u. In other words, vector v minus vector u minus vector v is equivalent to vector u plus negative vector v, or vector u followed by negative vector v. So again, you can use the head-to-tail method to find vector u plus negative vector v like this. Okay, have a look at the diagram here. This is how we can apply vector subtraction. Well, actually, if you like, you can also directly find u minus v using the tail-to-tail method. So in this method, you can translate vector v so that u and v are tail-to-tail, and draw a vector from head of v to the head of u, such that you find vector u minus vector v. All right, next let's have a look at another special case, which is adding opposite vectors and zero vector. So when you add two opposite integers, the result is zero, right? A similar result occurs when you add two opposite vectors. Consider vector p and its opposite vector, negative p. Then they have the same magnitude but opposite directions. To add these vectors, you can place them head to tail. The vector from the tail of vector p to the tail of vector negative p has no magnitude. This is called the zero vector, which is written as vector zero. It has no specific direction, which means the zero vector can have any direction. You understand? So be careful with the difference between the scalar zero and vector zero. Vector zero is actually a vector, not a scalar. But this vector is so special that it can have any direction. It has no specific direction. And the magnitude of this vector is zero. You understand? All right, then let's consider a example question. We are given two vectors, u and v. Can you find u plus v? And then find u minus v. Okay, I'll give you 5 minutes to think about this question by yourself. Okay, have you finished? Let's have a look at the solution. Remember, there are two methods to apply the vector addition, right? Method one is called the head-to-tail method. So we can translate v so that its tail is at the head of vector u. Then draw the resultant u plus v from the tail of u to the head of v. Therefore, we can find resultant vector u plus v. Okay, note that we can also use the parallelogram method. So in this method, we need to translate vector v so that vector u and v are tail to tail. Then construct a parallelogram using vectors equivalent to u and v. The resultant u plus v is the indicated diagonal of the parallelogram. Okay. Any questions? Any questions? No? Okay, then let's have a look at u minus v. Well, actually, there are three methods to find u minus v. First, we can use the head-to-tail method. In this method, we can draw a opposite of vector v, which is negative v. Then we can translate negative v so its tail is at the head of vector u. Then add u and negative v in order to find vector u minus v. The vector highlighted in red is your target vector, u minus v. You understand? Okay, method two is to use a parallelogram method. You can draw the opposite of vector v and place vector u and v tail to tail. Complete the parallelogram and draw the resultant u plus negative v. Again, in this diagram, the vector highlighted in red is your target vector, which is u minus v. The resultant is the indicated diagonal of the parallelogram, right? Okay, there is another method, which is a tail-to-tail method. You can translate vector v so that u and v are tail to tail, and draw a vector from the head of vector v to the head of vector u. Call this vector w. Then vector w is your target vector, which is u minus v. You understand? You can choose any method you like to find u minus v. Okay, any questions? Okay, if you don't have any questions, let's consider another example. Vectors in parallelograms. Consider the parallelogram EFGH with diagonals EG and FH that intersect at point J. There are two questions. Question A, express each vector below as a sum of two other vectors in two ways. Question B, express each vector as difference of two other vectors in two ways. Okay, I'll give you 5 minutes to have a look at this question. Hey, have you finished? All right, let's have a look at the solution together. Okay, consider question A. There are several possibilities for each vector. So two examples are shown for each. For example, HF can be expressed as HE plus EF, right? Or HF can also be expressed as vector HE plus vector HG. Okay, second, FH can be expressed as FE plus EH. Or FH can also be expressed as FE plus FG. Okay, third, vector GH can be expressed as vector G. Sorry. Vector GJ can be expressed as vector GH plus vector HJ, or vector GJ can be expressed as vector GF plus vector FJ. Any questions? Again, note that there are several possibilities for each vector. Okay, then consider question B. Express each vector as a difference of two other vectors in two ways. Okay, question A. HF can be expressed as HE plus EF, right? And vector EF is actually negative FE. So vector HF can be expressed as vector HE minus vector FE. Or vector HF can also be expressed as vector GF minus vector GH. And in question 2, vector FH can be expressed as vector FE plus vector EH, right? And vector EH is negative vector HE, so vector FH equals vector FE minus vector HE. Or vector FH can also be expressed as vector GH minus vector GF. And similarly, in question 3, vector GJ can be expressed as vector GH plus vector HJ. Also note vector HJ can be expressed as negative vector JH. So vector GJ can be expressed as vector GH minus vector JH. Or vector GJ can also be expressed as vector FJ minus vector FG. Okay, have a look at the solution here. Do you have any questions? All right, if no questions, let's consider another example question. Solve a bearing problem. In an orienteering race, you walked 100 meters due east and then walk east of nose 70 degrees for 6 meters. How far are you from your starting position and at what bearing? Okay, I'll give you 5 minutes to have a look at this solution, have a look at this question by yourself. Are you finished? Okay, then let's have a look at the solution. So we can use the cosine law to find the magnitude of vector r, right? From the diagram in method 1, we have angle ACB equals 90 degrees plus 70 degrees, which is 160 degrees. Then the magnitude of r squared equals the magnitude of AC squared plus magnitude of BC squared minus 2 times the magnitude of AC times the magnitude of BC times cosine angle ACB. And substitute all the numbers in. This gives us the magnitude of R equals approximately 157.7. Then we can use the sine law to find angle BAC. So note that sine angle BAC divided by the magnitude of BC equals sine angle BCA over the magnitude of R, the magnitude of vector R, right? So we have sine angle BAC equals the magnitude of BC times sine angle BAC over the magnitude of R. Again, put all the values in. This gives us angle BAC is arc sine 60 times sine 160 degrees over 157.7, which is approximately 7.5 degrees. Also note that angle BAC is relative to east, right? So we can convert to a quadrant bearing. 90 degrees minus 7.5 degrees is 82.5 degrees. So the conclusion is you have traveled about 158 meters from your starting point at a quadrant bearing of about east of north 83 degrees. Okay, have a look at the solution here. Do you have any questions? Okay, if you don't have any questions, let's consider the next example. Can you simplify each of the following expression? Well, this is pretty straightforward, right? You can do this using the properties of vector addition and subtraction. Okay, I'll give you 2 minutes to have a look at this. Okay, have we finished? Okay, let's have a look at the solution. Question A, the original expression can be written as V plus U minus U, right? This is according to the commutative property. Then minus vector U can be written as plus negative vector U. Then according to associative property, we can rewrite this to vector V plus vector U plus negative vector U. And the related part becomes vector 0, right? 0 vector. And U plus vector V plus a 0 vector equals vector V. This is according to the identity property. Okay, in question B, the solution is similar. So we can rewrite this to vector Q plus vector P minus vector P, then minus vector Q. Then that becomes vector Q plus vector P plus negative vector P minus vector Q, right? So that gives us vector Q plus 0 vector minus vector Q. And this can be written as vector Q plus negative vector Q. And final result is the 0 vector. Okay, do you have any questions? Okay, let's resume our class. Next, let's have a look at the multiplying a vector by a scalar. Given a vector V and a scalar K, where K belongs to the real number set, the scalar multiple of K and V, KV is a vector K times as long as vector V. Its magnitude is the absolute value of K times the magnitude of vector V. If K is greater than 0, then KV has the same direction as V. If K is less than 0, then KV has the opposite direction to vector V. A vector and the scalar multiple are parallel. So for example, vector 2V has double the magnitude of vector V and has the same direction. And vector negative 3U has the triple. Vector negative 3U has triple the magnitude of vector U, but has the opposite direction. Okay, any questions? Okay, if you have no questions, let's consider example. Represent scalar multiplication. So consider vector U with magnitude 100 kilometers per hour at a quadrant bearing of east of north 40 degrees, as shown here in this figure. Can you draw a vector to represent each scalar multiplication? Describe inverse the resulting vector. Okay, I'll give you 5 minutes to have a look at this question. Okay, have we finished? Let's have a look at the solutions. Okay, first, draw an arrow 3 times as long as a vector u in the same direction as u. Then the velocity is 300 kilometers per hour at a quadrant bearing of east of north 40 degrees. So that's the 3u, right? So for question B, we can draw an arrow half as long as vector u and in the same direction as the vector u. So that gives us 0.5 times vector u. Velocity is 50 kilometers per hour at a quadrant bearing of east of north 40 degrees. So for question C, we can draw an arrow twice as long as vector u, but in the opposite direction of to vector u. The velocity is then 200 kilometers per hour at a quadrant bearing of west of south 40 degrees. Okay, any questions? Any questions? No? Okay, if no questions, let's have a look at another important concept, which is called the collinear vectors. Vectors are collinear if they lie on a straight line when arranged tail to tail. The vectors are also scalar multiples of each other, which means that they are parallel. So the following statements about non-zero vectors u and v are equivalent. First, vector u and vector v are scalar multiples of each other, which means we can have vector u equals k times vector v, where k belongs to the real number set. Second, vector u and vector v are collinear. Third, vector u and vector v are parallel. So these three statements about non-zero vectors u and v are equivalent, which means the same thing, right? Any questions? Okay, then let's have a look at the vector properties for scalar multiplication. First, we have the distributive property, which means for any scalar k belongs to the real number set and any vectors u and v, we have k times the sum of u and v equals k times u plus k times v. Then we have the associative property, which means for any scalars a and b belongs to the real number set and any vectors v, we have the product of a and b times v equals a times the product of b times v first. Then we have the identity property, which means for any vector v, we have scalar 1 times the vector v equals vector v. Again, the rigorous proof of these properties involves the concept of Cartesian vectors, which we will learn in the next few lessons. So currently, you can try to prove these properties by yourself after this lesson, okay? Or you can try to prove these properties after we have learned the concepts of Cartesian vectors. Okay, do you have any questions? Okay, if no questions, let's have a look at another concept, which is called the linear combinations of vectors. Given two vectors, u and v, and scalars s and t belongs to the real number set. The quantity su plus tv is called a linear combination of vectors u and v. For example, 2 times vector u minus 7 times vector v is a linear combination of vectors u and v, where s equals 2 and t equals -7. Are you clear? A linear combination of 2 vectors is expressed like this. Okay, if you have no questions, let's have a look at the example. So here, let's consider this example. In trapezoid ABCD, BC is parallel to AD, and AD equals 3BC. Let vector AB equals U, and vector BC equals V. Express vector AD, BD, and CD as a linear combination of U and V. Okay, I'll give you 5 minutes to have a look at this question. Okay, have we finished? Let's have a look at the solution. Okay, first note that the length of AD is 3 times BC, right? And also AD is parallel to DC. So we know vector AD equals 3 times vector V, because vector BC equals vector V, right? And also we know vector BD equals vector BA plus vector AD. Therefore, that equals negative vector U plus 3 times vector V. And also we know vector CD equals vector CB plus vector BA plus vector AD. Then substitute all values in, we have negative V plus negative U plus 3V. And the final solution is negative vector U plus positive 2 times vector V. Okay, you have any questions? Any questions? Okay, so this is today's lesson. Then let's make a summary by revisiting today's learning goals. So now, after this lesson, you should be able to apply addition, subtraction, and scalar multiplication to geometric vectors in two space. Solve problems related to vector addition, subtraction, and scalar multiplication geometrically in two space. Then determine if vectors are collinear in two space. Next, understand the distributive, associative, and identity properties for scalar multiplication for geometric vectors, and apply them to solve related problems in two space. And last, understand the concept of linear combination of vectors in two space. Okay, if you don't have any questions, do not forget to complete your homework and submit them onto our Google Classroom before the deadline.